be able to distinguish between dark matter theories and my theory of gravity, which does not have dark matter. And indeed, I was amazed to find out that I can do this within the theory. So, without getting into too many technical details, what happens is that you calculate from the structured growth as galaxies are being grown. The structure of the universe is beginning to appear after 400,000 years after the Big Bang. And if you use Einstein gravity to calculate what's called the power spectrum, this is the amount of power, the strength of light coming from galaxies in the sky, and there are millions of them, and you calculate the amount of power coming from them, the amount of light being produced by these galaxies, and you get this vertical axis here versus what's called the wave vector. This K, this is the very early universe, this is a late time universe. If you use Einstein gravity without dark matter, you get this dotted line result which simply doesn't fit that data there. Put in my mug and you get unit oscillations occurring because the baryons oscillate. If I have a ball, tennis ball made of baseball, made of baryons, which it is, and I throw it on the ground, it bounces. If I have a baseball made of dark matter particles, it just goes right through the floor because it's collisionless. Okay? So this has this effect that this curve here is the result obtained from the standard dark matter model in cosmology. It's a smooth curve. So what happens is that you have to put in what's called a Windle function to the data analysis, and we get the red result, which fits the data just as well as the so-called lambda CDM, standard model cosmology. So you wait around and count more galaxies, and eventually you will see this. So that's it. You sit and wait. And I have a bet out with Professor Jim Peebles, a well-known cosmologist in Princeton, that we will see me, the red result. He claims you will see the blue, which is the standard model cosmology with dark matter. It's only a $10 bet. I wanted to bet more, but he refused. This is the log of mass of any body in the universe versus the log of distance. And this is where Mark can fit the data over 14 orders of magnitude in mass. This is quite remarkable. There's another test that can be done. Because Mark, we published a paper, Victor Toth and I published a paper in the monthly note of the Royal Astronomical Society just some months ago. And we claim that we can understand the origin of inertia. This is a very fundamental problem in physics since Newton. I don't think Newton understood really the origin of inertia. Inertia means that if I kick a table, it doesn't move. Okay? If I kick it hard enough, it moves, according to Newton's law. And there's no complete understanding of this in Newton's gravity theory, nor in Einstein's gravity theory. But in my MOG, we can understand it. And this gives rise to an experiment which is going up in the Pathfinder spacecraft being launched by the European Space Agency in 2011. It's a very simple experiment. It's all there in the spacecraft. And what happens is that at small accelerations of this order, about 10 to the minus 9 meters per second squared, you see a violation of Einstein's equivalence principle, which I talked about earlier. So if you see this, then Mark is correct. It's really very difficult to get any other theory to give this result. So this is a prediction. Okay, so finally we get around to the issue of dark energy. Remember that the universe consists of this dark energy, supposedly. which is uniformly distributed throughout space-time, whereas dark matter clumps. It clumps because it's producing galaxies. The dark energy doesn't clump, it's just uniform like an ether. And do I understand what it is? No. Can I detect it? No. It can be vacuum energy, the so-called Einstein cosmological constant, which he introduced in 1917 into his field equations in order to make the universe static. He didn't want the universe expanding. Unfortunately, he didn't go far enough, because this would have been an amazing prediction of his equations. This was left to the Russian mathematician, physicist Friedman, and Lemaitre, the Belgian physicist Lemaitre, to predict that his equations were dynamical. The universe is expanding. Galaxies are receding from us, as observed by Hubble in the 30s. So this cosmological constant rears its head again because it's used in the standard model of cosmology to fit the fact that the universe, expansion of the universe is accelerating. So there are hundreds of papers being produced trying to explain this. Constant flow of papers, a lot of controversy about it. And the cosmological constant is not a happy thing, because when you calculate it in particle physics, which I can do, calculate the amount of vacuum energy, the vacuum is not just empty, it consists of particles and so-called antiparticles, say electrons and positrons, positively charged electrons annihilating one another. And so it's a teeming mess of particles and antiparticles annihilating one another. They annihilate one another, so therefore you, according to the Heisenberg's uncertainty principle, you can't see. It looks empty. The vacuum looks empty. Anyway, when you calculate the value of this thing from particle physics, it comes out 10 to the power 120 times too big. It's the most disastrous prediction in the history of science. It's ridiculous, okay? Even if you try to improve things, you still get powers of 10 to the power 56 times the observed, so-called observed vacuum energy, which is needed to explain the acceleration of the expansion of the universe. This is unacceptable, because you have to fine-tune the calculations for this lambda to 56 decimal places, so maybe 120 zeros, okay, after the decimal point. This is simply unacceptable. So something is badly wrong. And this is one of the other great problems of modern physics. This nasty problem called the cosmological constant problem. I spent some years working on this, and I tear my hair out trying to understand it. So does everybody else. There are a lot of theories about how this should be improved, and everybody disagrees with everybody else about whether they have the right answer at the present time. So, then I have different uniforms I wear. This was my modified gravity uniform. Now I put on another uniform called Don't Modified Einstein Gravity. So, in 1992, I was the first to do this. I produced a phenomenological model of cosmology called the Void model, published in the Physical Review and just a physical journal with my student Tatarsky. And in this model, what we see out there when we look at galaxies, distribution of galaxies through large-scale surveys, is huge voids, 35 million parsecs. One parsec is 3.26, about 3 light years. Okay? And if you have these voids, if we're sitting near the center of a void, then I predicted that light coming from distant sources, like galaxies, would be dimmed, because the space-time inside the void is expanding faster than outside, because there's nothing in there, so there's no very little gravity.